by Qiang from UT Austin, splitting gradient descent for incremental training optimization of neural structures.
Thank you very much. So this is some of the new ideas that we came up for optimizing neural network structures using some ideas from functional gradient descent. So we have been talking a lot about the parameter optimization of neural networks, but optimizing the architecture or the structure of the neural network, meaning the number of nodes of different types of neurons and in different layers, is also, in fact, an even more important problem in deep learning, right? So often, from the empirical studies, we find that a dramatic improvement sometimes can be obtained by discovering new types of neural networks. Right? So optimizing neural network structure is also a key bottleneck for automatic machine learning, where we need to automatically decide the structure of the neural networks for the given data sets that we have. Right? In addition, for energy efficient settings where we are interested in learning small, compact neural networks that have fast inference time and energy assumptions for applications such as mobile devices, Internet of Things. In this case, we want to have small network that run on the things like mobile phones, so that we need a very low energy cost. Right? In this case, architecture search algorithm would be very important for balancing accuracy and computation cost. Unfortunately, architecture optimization is a very difficult problem. So it's a discrete optimization problem. It's a combinatorial optimization when it's very large search space, very expensive evaluation process, right? And mostly in the literature, even though we have developed a huge literature on architecture search, most of them are based on black box optimization procedures, such as the evolutionary algorithm or policy gradient reinforcement learning in general. These algorithms does not really leverage the fundamental mathematical property of this problem, this optimization problem. In fact, it appears that that's almost no mathematical structure there that we can exploit mathematically in order to derive new algorithms. And this work is motivated by sort of developing some mathematical motivated ideas for solving architecture search. In particular, we are going to develop something that is very similar to gradient descent, but for structure optimization. So we will leverage a very simple idea that, in fact, we can view the co-optimization of the parameters and the structures as a function optimization problem in the space of distributions. So it's a simple idea. So I will explain very quickly what it means. And then we will develop a quite practical and simple algorithm that, in fact, incrementally grow a neural network iteratively by splitting neurons into multiple copies. So I will also explain what this means. And then in the end, this algorithm is actually quite practical, fast, and allows us to get compact and accurate architectures for many practical problems. So here's the key idea. It's a very simple idea. So the problem is that we can actually, because the neurons are exchangeable, right? So we can view the optimization of the weights as optimizing over the distribution of the weights. And because the distribution of the weights encodes both the number of neurons and the parameters, and if we search through the distribution space, we are automatically optimizing the structures, right? So more specifically, here's a simple problem, example, where we have a simple two-layer neural network. Theta I are the weights of the neurons, right? So typically we formulate this optimization problem. Capital Phi is some loss function, and E is the distribution of the distribution of the data. And then because the neurons are permutable, we can actually equivalently parameterize the neural network using the distribution of the neurons. So rho represents the empirical measure of the neurons, right? And then the function, now the neural network is now parameterized by the distribution rho. taking the expectation of the neurons. And then the optimization can be relaxed into an optimization over rho, the distribution, right? Again, because now the distribution, so if you change the distribution in some smooth way, you can actually also change the number of neurons, right? And in this way, if we search through the space of distributions, we can actually search through different types of architectures, right? So this is the idea. So if the rho is actually an empirical measure, if we can actually have a way to maintain rho to be an empirical measure of finite number of particles during our search space, then we will get a practical algorithm, right? So this idea can also extend it naturally to more general cases when you have multiple types of neurons or neurons in different layers. In that case, we just have a joint optimization of a bunch of weight, distribution of weights, right? So here, rho I represents the distribution of the weights on the ith layer, right? Okay, so we want to solve the optimization. Let's review what's happening for the parametric case. In most of the cases, we use steepest descent for optimizing parameters, right? We're going to extend steepest descent for the functional space in a practical way. But let's have a very brief overview of the parametric case, right? So the idea is that iteratively at each iteration, we update the parameter theta t to theta t plus 1 by finding the optimal, the fastest descent point within a small neighborhood of the parameter from the last iteration.
How do you, I mean, the loss of theta should be the loss that you will incur if you use this architecture.
Yeah.
So how do you have access to it? I mean, it seems like for every theta you will have to train the network in order to find out what this loss is, and even then.
No. So here the loss is indexed by both the parameter and the architecture. So you don't need to train that. Right. So given an architecture, you do need to train to find the optimal theta. But here, the rho is encoding both the architecture and the parameter, so you don't need to train it. Right. So it's a parameter and structure co-optimization.
I'm sorry. So the rho here is a bunch of delta functions, sum of delta function, or the rho is smooth?
Rho is actually a delta measure. Yes.
So
a bunch of delta functions.
It has to be delta measure.
Yeah. So we will have actually a way to make sure it's always a delta function within the optimization. Yeah. But going back to the parametric case, this is standard, right? So if we do steepest descent, which means you want to find the optimal points within a small neighborhood of your solution, then in the non-station points, we have the gradient descent, gives you a first order improvement, O of epsilon. And then at the non-stationary saddle points, non-stationary point, at the saddle points or non-local, the local optimum, local maximum, then we have this eigen descent where we follow the eigen, minimum eigen direction of the Hanschen matrix, which gives us a second order descent. Now, in practice, we now already know that we can just escape the saddle points using random initialization or random noise without calculating the eigen directions. And then the algorithm will converge at a local optimum, local minimum. Right. So we want to do things that is parallel to this for the functional case. And the idea is simple. So here's a simple generalization. We are still doing steepest descent, but now we are doing it in the space of distributions, right? And here we need to actually define some notion of distance. The distance has to measure the difference between two different distributions. So here the key is really that we want to choose the distribution, the distance, so that we can actually get a practically imputable algorithm by following this derivation. What that means is that I need to choose the probability metric properly so that if my rho t is an empirical measure of a finite number of neurons, right, which corresponds to a practical finite size neural network, then following this derivation my rho t plus 1 has to always also be a finite size neural network. And I also want to make sure that from rho t to rho t plus 1, the computation is fast as something like gradient descent. So I can actually practically implement this algorithm. Right.
Yeah, I think I'm having a question related to the previous question, but to make it exactly more concrete. So just for the sake of example, if you had a neural network with a single hidden layer, and the only architectural modification
is the number of neurons.
Extra neurons, right? So in that case, what is rho exactly? Because all I'm thinking is the number of neurons is the extra parameters, and the additional, and that comes with an additional set of weights.
Yes.
And so what d distance would I use between the distributions, and what would that mean in that particular example?
So I will talk about that in the next slide. So we are just going to use the Waterston distance. So in that case, if you have let's say one hidden layer neural network, then the weights are really a bunch of points, right? Even though you cannot determine the number of points, but then for two sets of points, you can calculate. You can view them as two distributions and calculate the Waterston distance. So this is what I mean. Right. So okay. So we decide to use Waterston metrics for the properties that we wish on the last slides. So basically, so here's the p Waterston distance. So for given two distributions, rho and rho prime, which could be just two sets of points. And then the p Waterston distance is the minimum transport cost measured by the LP norm, right? And then we also have the infinite Waterston metric, which is the case when p goes to infinite. So this is the case when instead of using a p norm and taking expectation over the coupling, we actually just take a shoop over the pairs, right? So in this case, we are trying to find the minimum worst case distance for transportation. Right? For both of these two cases, we can sort of visualize the structure of the neighborhood of these two cases. For finite p, for any given probability mass, let's say this dot represents a neuron, for the epsilon neighborhood of p Waterston would allow you to arbitrarily move the probability mass within this epsilon neighborhood. So in this case, this probability mass is split into three locations with smaller weights, right? But because we are taking p norm here, and it's an expectation, so we can also actually move this probability, a very small portion of the probability mass, into somewhere that is very far away from the original points, right? And this is because the cost is measured by the expectation, right? But this non-local update is actually something that we don't want, because within the algorithm, we only do local search. We don't want to do a global jump that will require some higher computational cost to solve an inner loop problem. So in order to eliminate that, we actually decide to use infinite Waterston metric. So in this case, any given probability mass is allowed to transport arbitrarily within this epsilon ball, which is local update, but it can never go outside of the epsilon ball. Right. So this is some good candidate for our algorithm.
Sorry, so rho is a signed delta measure, right? So it's a signed therefore because of the WI. So how do you sample with?
So here we actually assume, let's say WI is always positive, because you can always scale them properly.
You will assume this also later? Always the WI is negative?
So we just assume that.
Okay.
Yeah. But it doesn't influence the practical algorithm.
Okay.
Yeah. Okay. So then if we just use the infinite Waterston distance, and we can follow the formula that we had earlier to derive the steepest descent, that's a standard procedure to do that. It turns out if you work out it, we can find that this infinite Waterston steepest descent is a combination of two types of updates. One is that it obviously contains parametric steepest descent. What it means is that at the non-station points, we are going to update the parameters just by minimizing the parametric loss without introducing changes over the structures. Let's say you have n particles originally, we will just keep the n particles and just update each particle using gradient descent. So this is a standard gradient descent without structural change. And then, in addition to that, in terms of neighborhood, this is corresponding to just moving the probability mass without splitting. Right?
Just a quick question. So earlier today, we heard about one of your papers with Tong Yu and with Jason and with Colin Wei.
Right.
So this is basically a discrete version of that algorithm?
No, that's not related. That's totally different.
But that one also has a Wasserstein distance.
That's a Wasserstein 2 distance.
This is also a shallow network, no? There are
No. This can be extended to more general deep neural networks. So I can comment on the difference between two Wasserstein versus infinite Wasserstein networks.
But the version you're presenting now, will this be a multi-layer one or a shallow one?
It will be a multi-layer one. I will explain later. Yeah. So I promise you, it will be obvious to extend this to multi-layer ones.
Computationally efficient.
Yeah. Okay. So it includes two parts. One is the steepest descent. Another is splitting. So splitting means that in addition to just moving the particles, we can actually also split the particles. Because this is not allowed in the original Euclidean space, but it is allowed in the functional space, because now we are viewing these neurons as particles, right? So more specifically, let's say we have a theta, which is the neuron, and have a weight magnitude W. We can actually split the neuron into a combination, a bunch of theta I and Wi, such that the sum of the weights equal to W, right? And then we can also, so the theta I would be different from theta. So in this case, we are actually augmenting the structure of the neural network. So it turns out, I will show the derivation later, it turns out this types of update only gives you a second order improvement, meaning that this kind of update only happens at the stationary point. So at non-stationary point, you are going to just do a typical gradient descent. At the stationary point, then you actually has the option of performing a splitting, right? And then it turns out what's happening is that this kind of operation, the splitting, allows us to escaping saddle points in the Wasserstein space, but local optimal in the Euclidean space. Let's say you run a standard gradient descent and it converges, and that means just by updating the parameters, there's no way to improve the algorithm, right? And then in this case, we can actually introduce splitting, which means we are going to introduce new neurons, and that actually in this higher dimensional space, that's actually it's possible that there are directions that allows us to further decrease the loss, right? But with the cost of increasing the size of the neural network. So here's, in terms of neural network, here's what's happening. Let's say you have a neuron, and then what we can do, the operation we're introducing is to copy this neuron into two copies, and then each of them receive a portion of the weight. And then we can update the parameters of these two neurons jointly, right? So here's a plot that I think is very intuitive. So basically what's happening is if you are running a standard gradient descent without changing the structure, at some point you will reach a local optimum. That means you can no longer update your, you can no longer improve your loss by just updating the particles, right? So it's, think about each of neuron is a ball like this, right? So there are actually two cases in the station point. One is in this case where you are pulling the ball into the opposite direction. So in this case, if you actually split the ball will actually separate and the energy will decrease, right? So this is the splitting unstable case. This is the case we can actually improve the neural network, improve the accuracy by splitting the neural network, the neurons. And this is the case of splitting stable, which means that even if you split the ball from the middle, because the forces are pushed together, the update there will be no update. Even if you push them away a little bit, they will be pushed back, right? So the question is, can we actually identify these two cases, right? And then in the case of unstable, the instability case, can we actually derive the optimal update strategy.
So I guess supposing a standard parameterization, you split. Suppose you are at a local minimum,
Right.
and you split one neuron into two
Yeah.
by copying the
Yeah.
associated weights.
Yeah.
That's still a local minimum, right?
It is local minimum in the parametric space.
Yes.
So, no. So it is so let's say if you have one neuron, right? Before splitting, you have one-dimensional Euclidean space. In that space, you are reaching a local minimum. But after you split, you get 2 dimensions. So in the 2-dimensional space, it could be a saddle point, because the additional dimension could be either stable or unstable. Right.
Okay, so that can even happen in the parametric space as well.
If you increase the parameter space.
Got it.
Okay. Okay. So I think here might be an easier way to understand all these things without a functional analysis. So here I'm actually going to do a very simple case, just a single neural network where we just have a single neuron sigma theta x, right? In this case, the loss is a very simple function like this. And then assume we actually split this neuron into m copies, theta I, and then each of them has a weight wi, right? And then in this case, we get an augmented loss. The loss is going to be a function of both theta and w. And then it's by replacing sigma theta x with the weighted sum of the copies, right? Obviously, if you take theta I equal to theta and wi equal the sum of wi equal to 1, then the augmented loss equal to the original loss, right? Meaning that even if you split, you keep the weights to be the same, you get the same network, right? So now in order to derive the steepest descent, what we need to do is to actually optimize this augmented function. So we need to choose the optimal number of copies, m, right? As well as the values of each copy and the weights, such that the loss is minimized, augmented loss is minimized. So here we have this constraint that for every copy, theta I minus theta has to be smaller than epsilon. This is because the infinite Wasserstein neighborhood, right? And then sum of weights equal to 1, right? Any question about this? Okay, so it's a very simple optimization formulation. And then it's actually a simple problem. So in order to derive the solution, it's convenient to decompose the difference between theta I and theta into the sum of delta average, which is the average displacement of all the copies, right? As well as delta I, which is the individual splitting direction. So such that the weighted sum of the delta I equal to 0, right? So what it means is that if delta average equal to 0, I'm not updating the overall average of the particles. I'm just splitting them into opposite directions, right? But if you have the delta average, so the overall average is also updated. And then with this, we can have this simple Taylor expansion for the augmented loss. It turns out the augmented loss equal to a sum of 2 terms. The first term is the effect of the average displacement. What this means is that it's equivalent to just updating the parameter without splitting, just keep the original neuron, and just update it by delta average, right? So this is going to be a standard gradient descent, right? And then the second term is the effect of splitting. So what this term is, this term is actually a weighted sum of quadratic term, which depends on delta I, which is the individual splitting direction, as well as S theta. S theta is some matrix that I call splitting matrix, defined in this way. It is a semi-Hanschen matrix because by definition, it's going to take the first derivative of phi, which is the loss, and then take the second derivative for the neural network. Right? So this will be a d by d matrix where d is the dimension of the parameters of the neuron. Right? So, and then following this, because we are decoupling the displacement and splitting, we can try to find the optimal splitting strategy by minimizing the second splitting term, right? Now, because it's a quadratic term, it's very easy to say that the optimal splitting strategy is actually just splitting each of the neuron. If the minimum eigenvalue of S is smaller than 0, right, then we can actually, the optimal solution would be just splitting each of the neuron into 2 copies with equal weights. And the update direction of each neuron is going to be just follow the eigen direction of the minimum eigenvalue for S theta, right? So in this case, it has this simple structure so that it's both sufficient and optimal to split the neuron into 2 copies with equal weights. And then if the minimum eigenvalue is larger than 0, then no splitting can decrease the loss. In this case, it's splitting stable, meaning that no matter how you split the neurons, it's going to be stay the same. Even if you split epsilon away, it will be pushed back if you further update.
So one of the standard ways to escape saddle points is to follow the negative Hessian directions. Are
Yeah.
you going to compare to this in your experiments?
So this is different, right? So
I'm not asking if it's the same or different. I'm saying, are you going to compare the two in your experiments?
no, I'm saying the setting is different, right? One is when you have a parametric optimization, you are not increasing the parameter. You just split. You just decrease by eigen direction. But here we are actually increasing the parameters. So 2 slides away, I guess I have an answer for your question. Okay, so here we have this. So here is just another comment about the splitting matrix. So it has a very interesting structure that has the mix of first order derivative and second order derivative. It's very similar to Hessian matrix, except that the Hessian matrix has an additional term, right? By chain rule, it has S theta, which is the first term, and the second term is actually taking the second derivative for phi, and then first the derivative for sigma, right? Now, one important comment is that S is actually an easy part of the Hessian. I will show why this is the case, meaning that it's actually much easier to calculate S than T. Yeah.
Oh, sorry. So T is not PSD. Okay.
Yeah. T is T is the missing part of the Hessian, right? So. And the reason T is more complicated is because, let's say if you have a huge neural network where sigma is only one of the neurons, then capital phi is going to be highly complicated. You don't want to take a derivative for phi, and it's easier to just take a derivative for sigma, which is a simple neuron. Okay, so, and then now we can actually characterize stability in the Washington space. So being stable at Washington space means that no matter how you update your parameter, and no matter how you split your parameters, once the update is in the local region, you are stable. You can never decrease the loss, right? So from here, we can show that the Washington stability actually equals to the standard parametric stability, which is the fact that you can never update your parameter to increase the loss, right? Even by skipping the saddle points, right? And then the second part is the splitting stability, which means that even if you are allowed to split into 1 million or thousands or any number of neurons, you can never improve the performance. So it's a stronger notion of local optimal, right? Then so these 2 notions are really orthogonal in general. That's no general relation that imply one or another. But if capital phi is actually convex, which is the case of one hidden layer neural network, then the splitting stability actually implies the parametric stability, meaning that if you cannot split, then you can also not improve by just escaping saddle point. The parametric stationary point is actually optimal. Yeah.
So I guess when I played with some of these kind of ideas, in a slightly different context, so I found that this S matrix is almost never PSD. like in your sense, basically you can always split in some sense. Is that what you found in the experiments?
It is sometimes, but I do find the cases you cannot split, and it's not open. It's not global optimal.
And this is because this the sigma in the definition of S, right? So the second the Hessian of the model, that's always non-convex, right?
You mean this one, non-convex? May or may not, because let's say if you are using RaLu. RaLu is convex, but your weights could be either positive or negative, so it's unclear whether it will be convex, right? So, and because this part, this derivative part can also be positive or negative, so the combination, really the combination decides the overall positivity. So it's unclear how to decide it theoretically. I also studied this and tried to figure out if that's a relation, but it seems quite difficult.
Can you remind us what phi means in these two expressions?
Sorry?
Can you remind us what phi means?
Okay, yeah. Phi is the loss function. So, so I'm just assuming, let's say, the overall loss function equal to the neural network pushed into a function phi. So it could be the quadratic function in the case of mean square regression or logistical loss.
So its argument is a real value prediction, is it?
Yeah.
So what does phi of theta comma x mean? I think there was one of those that showed it.
Phi,
on
this
the
one.
slide that we were on. No.
Which one?
The slide that we. Yeah. Right.
Phi
So what's phi prime of theta comma x?
Phi prime. Oh, sorry. It's a typo. It's a typo. Yeah. It's a typo. It should be this way.
Again for a single.
Yeah. Single variable. Yeah. Okay. So now this is the case for the general deeper neural network. It turns out exactly the same relation holds. Right? Let's say you have n different types of neurons or n different layers. So this theta superscript n represents the nth neuron, right? Or nth population of neurons, because each neuron can have multiple copies. And then for each of this neuron, we can split it. Let's say just split it into multiple copies with different weights. Then the overall augmented loss is going to again equal to the loss you will get by just updating along the average direction without changing the structure. And then you have this splitting term, which is really just the sum of the splitting matrices of the individual neurons, right? So it's a very good result. Basically, it shows that that's no crossing term in the splitting matrix. So this is another reason I'm saying the splitting matrix is the easy part of the Hessian matrix, because there's no crossing term. And this is the key, because now you can calculate all these things quite efficiently. And you can also just directly compare the splitting matrices of different neurons, right? Let's say I have 3 layers, or then for each layer, then for the neuron of each layer, I calculate the individual splitting matrix. I can calculate the individual eigendirection, eigenvalues, and then I can compare them directly. This allows us to jointly decide the number of neurons in each layer. So this is the overall algorithm. Yeah.
Can you go back? So that was exactly wondering how the objective is used to decide the number of neurons. So how do you decide ML? MSAVL, like the number of...
oh, yeah. It's always 2. It's always 2 because by this derivation, if you want to optimize this weighted average of these quadratic things, the optimal splitting is always just split it into 2 copies. And then each of the copy follows either the eigendirection or the opposite of the eigendirection. So that's no need to actually split into multiple copies. So this is the overall algorithm. So what we are going to do is at each iteration, we just run standard gradient descent until a local optimal is reached. Because if I'm at a settle point, I can always just update the parameter to improve the performance. There's no motivation to split, right? So I will just run either stochastic gradient descent or any other algorithm until a local parametric location is reached. And then I calculate the splitting matrices for all the neurons that can be splitted. Right? And then I will just pick the neurons with the most negative eigenvalues, minimum eigenvalues, and then split these neurons, following the splitting all these neurons into 2 copies with equal weights, and then following the eigendirections of the minimum eigenvalue. Yeah.
What does it mean, eigenvector direction? Because you have one layer and you just split one neuron in.
So let's say you have let's say you just have one neuron, right? So then for this particular neuron, you can calculate that splitting matrix, right? Which is a D by D matrix, where D is the number of parameter of that neuron. And then you calculate the eigenvector of minimum eigenvalue for that matrix. And then you create 2 copies of the neuron. One is plus the eigendirection, one is minus the eigendirection. Makes sense?
This is the direction in what space?
In the parametric space. So let's say you have some parameter theta, right? Theta is going to be the weight of the neural network, right? And then you calculate this splitting matrix using the formula I showed on the slides. This is going to be a D by D matrix. Right? So the weight is RD, right? Right? And then you calculate the minimum eigendirection of this matrix, which is going to be V mean, right? Which is going to be a RD vector, right? And then what you do, when you split this theta into 2 copies. One is theta plus some epsilon step size Vm mean. Another is theta minus epsilon Vm mean, right? Each of them has a half of the weight. Right? This strategy is actually optimal following the derivation.
I'm sorry, so I'm very confused. So this, which neuron are you splitting in this? This V mean, can you locate a neuron? I mean, V mean is distributed, right?
Sorry?
V mean is distributed over all neurons.
Each neuron has a V mean. So let's say you have 10 neurons.
V mean, I see.
Yeah.
So are you in the single hidden layer setting or?
Arbitrary. Let's say you have a neural network with 1 million neurons. Just for each of the neuron, you calculate V mean. You will get 1 million V mean, right? And then you just split for this neuron that has negative eigenvalues.
I see.
Yeah.
And the dimension of this matrix depends on the fan-in.
Yeah.
So
it could be large, but it's much less than the overall size of the neural network.
I'm just saying finding an eigenvector.
I will address that problem.
Which is like 1,000 by 1,000.
I will address that problem later.
So does this relate at all to sort of, these ideas of doing like Frank Wolf descent?
Yeah, it is.
Is this sort of like taking a second order approximation?
No, actually, that's very, so it's very related. It turns out Frank Wolf is doing steepest descent when Wallerstein zero distance, which is equivalent to TV distance, total variation distance. But we are doing Wallerstein infinite distance. And the reason we are doing this is because it only gives you local update. If you are doing Wallerstein, if you are doing Frank Wolf, you need to do the global update. At each iteration, you need to add a new neuron by solving a global optimization. And this is exactly because for finite P Wallerstein, you have this non-local update.
How much reduction in the loss is it gain, and how does it depend on epsilon?
So the reduction is going to be epsilon square lambda mean.
And how do you know when to stop?
It has to be empirical. Let's say lambda mean is smaller than some threshold.
You've left out the residual term.
Which means
It's going to be scaled by. I mean, that's the Hessian of the ReLU, and then it's the epsilon square, which is the step size. But you have another. Yeah, you're dropping.
Yeah. So you're
using the Taylor expansion. You're dropping one of the terms.
this term?
next slide. No? Aren't you dropping one of these terms here?
This one? This is irrelevant to our algorithm because it's for
You're
parametric.
using S, no?
Yes, so it's the same, right? So basically, I'm saying that the optimal of this term equal to this, minus this. So this is the improvement of the loss by doing splitting. Okay, so this is a simple visualization of our algorithm. Let's say in this case, we are actually using a mobile net on Sapphire 10, starting from a small network. At each iteration, we run through all the layers and calculate the eigenvectors, and then decide which neurons I should split, right? By splitting neurons in different layers, we will end up with an architecture that is very different from the original one. Then you can sort of say the accuracy increases. This green curve is what you do if you increase the size uniformly, right? This dashed line is the full size case, and it's actually reached much earlier than the uniform case, splitting. So I know the Eigen calculation is a big problem. So we have an efficient approximation for solving it without actually expanding the splitting matrix. So the idea is really just minimizing the Rayleigh quotient. So we define this ratio, and then we find the optimal V to minimize it. The minimum value is going to be the minimum eigenvalue, and the solution is going to be the minimum eigendirection. And then we can do gradient descent or any other numerical algorithm. During this process, we need to evaluate this matrix vector product, which is the splitting matrix times some arbitrary vector V. It turns out this can be actually calculated quite conveniently by using an auto differentiation trick. The idea is that you construct this f function, which is constructed by adding an extra term on the output of each neuron. So this can be done in TensorFlow or anything else. You just compile this neural network, and then if you take the gradient for this function at y equal to 0, you will get this product, right? So, and what's nice is that if you have a large neural network, you can actually add this term into the output of each individual neuron, and then you will get overall function. If you just take a gradient for that overall function, you calculate this product simultaneously for all the neurons, right? And the computational cost is almost the same as doing backpropagation of the original network. So if you perform this overall process, you will get an algorithm that practically runs almost the same computational cost as performing a standard gradient descent. Yeah. Okay. So now we have some empirical results. So here's a simple toy example. X-axis is the number of iterations of the gradient descent. So here we are splitting starting from one single neuron. You can sort of see that these cliff points is when we are splitting the neurons. And you can sort of see that it really looks like escaping a saddle point. And then that's a bunch of baselines. So here's a visualization of the splitting process. So here we are training an interpreter neural network recently proposed in which case, so this neural network has a special interpretable layer, in which case the weights of each neuron is enforced to be similar to realistic data sets. So you can visualize the neurons. Right? So here we start from one single neuron, and then it can you can say it's blurry, likes nothing. And then it's split into two neurons that is less blurry. And then at this point, you need to decide which neuron to split. It turns out this one is selected. So it's split into two neurons that is similar but less blurry and more interpretable. And in the end, this one is evolved using gradient descent to be a 3. And then this one is further split into something that is like 6 and 9, and then doing gradient descent. And then next step, we decide to split 0, which evolves to something like 7 and 0. And then this process evolves until at some point we are doing good. So this is looking at a particular step. In this case, we have 3 neurons. And then what we did is we calculate the eigenvalue for each of the neurons. So we have 5 of them, right? And this pink bar is the eigenvalue. And this green thing is the actual loss if we end up splitting each of the neurons, right? We can sort of say that the eigenvalue and the loss is correlating well. For these two top ranked neurons, we can sort of say that they are actually splitting into something that is different, meaning that you are getting significant gain. Whereas for this one, if you split it, you will get the same thing. Means that there's no improvement. Right? So it is doing something that is fairly reasonable. So here we have a comparison with pruning methods on Cypher-10 dataset. So the idea is that our method is growing the neural network, starting from a small network and gradually increase the size, right? There has been a bunch of algorithms that trying to do the opposite, in which case you train a large neural network and gradually prune the unimportant neurons, right? So these 2 curves represent 2 of the recent pruning-based methods. And it's interesting to see that our splitting method is actually can be better than these pruning methods, even though the pruning method is actually leveraging the full-size model, which has more knowledge and slower. And then finally, we have this example on the keyword spotting. So this is when...
Sorry, can you go back? Yeah. What about the time for pruning versus...
we didn't explicitly compare. It would be great to compare, but I don't think they are very different. Because the pruning, you need to actually start from the full... Yeah. And then this is an example of keyword spotting. In this case, so basically every time we use Google Assistant or any other intelligent assistant, you need to wake up the system by saying some words like, OK, Google, hello, Google. And this is detected by keyword spotting algorithms, right? And this kind of algorithm need to be divided on, deployed on edge devices, and has to be on all the time in order to wake up anytime, right? So this is obviously very energy consuming. So a challenge has been developing small size neural network that can still detect these keywords with high accuracy. So here we use a recent benchmark by Qiang et al., and we can see that our method can be better both in terms of accuracy, number of parameters, and number of flops. Thank you very much.
What was your architecture? So it's always fully connected?
Oh, no, it could be all kinds of architectures.
So CNN or RNN?
Yeah. Anything else. In case of CNN, we're actually splitting the channels.
Just channels?
Yeah.
Did you find any needs to control the number of splits?
Yeah, we do need to control. Basically, we use heuristics like every time split some amount so that we don't get like grow up or something. Yeah.
How sensitive is your final architecture to your initialization?
Can you repeat the question?
How sensitive is the final architecture with respect to the initialization? I don't really know. I think we should study that because often we just do one. Because for this kind of deep learning experiments, it's fairly expensive. So we basically just take a standard benchmark and then shrink its size proportionally and then just grow. So I don't know how to make a kind of reasonable starting point, but that's a very good question.
So you don't always start from uniform. In the example you showed, you have the uniform.
It's actually not uniform. It's a mobile net shrinked proportionally, so it's not exactly uniform. Yeah.
Can this method be extended to splitting layers?
So what's the question?
Splitting layers.
Splitting layers, yeah, it's a very good question. I don't know. Splitting layers will be a fundamentally different question. So here, splitting neurons is a second order thing. So you only need to split at the stationary point. And this is very nice because you can run gradient descent and then split. But if you are splitting neuron layers, it turns out it's actually a first order thing, meaning that if you derive a functional algorithm, a gradient descent algorithm, it will always split. So I don't know how to make it practical yet. But it's a very good direction.
question, how to make the visualization for the emptiness? If the two image means the theta plus the epsilon eigenvalue, or
this one? Yeah. So each of the image represent the weight of each neuron. Yeah, so this is one neuron, and if we split it and run gradient descent until it converges, this is the value of the other two neurons. So, and this structure is actually a special structure. If you just run fully connected, you wouldn't get such interpretive model. You need to do something special. You need to enforce these weights to be similar to realistic images.
So the weights look like the...
Yeah.
Okay.
Yeah.
And do you make the experience, so for your final neural network, you train it from the beginning and compare with the accuracy you achieve now, which one will be better?
Could you say again? What's the question?
So you already, eventually you get a bigger network, right?
Yeah.
So for this bigger network, you can train it from scratch.
Yeah. We actually did both. So it turns out training from scratch actually improved a little bit. Okay. We don't know why, but yeah.
Okay. Yeah. All right. Or do you only do splitting? Do you also can somehow merge the neuron?
No, because that's not allowed in the functional gradient. Okay. So even though you can do it practically, but it's not a part of this algorithm. Yeah.
So I guess maybe the last question.
Have you tried reconstruction like deconvolution network kind of problems?
Deconvolution?
Yeah, kind of.
We are actually trying something like that. We haven't got that far yet. Yeah. But it's very interesting.
Okay. I guess I thank the speaker again and.